And so what that says is, all this says is that y prime is equal to a. But y prime is dy dx. Okay, right? And so if I give you the differential equation dy dx is equal to a, that means that y of x has to be equal to ax plus another constant, let's call it b. So that's the equation of a line. So we got from variational calculus that the curve that connects 2 points and has minimal arc length is a line. But we knew that already. And if you wanted to find what is the specific line that satisfies these two conditions, then you would put in x1 and you would get y of x1 over here, and you put x2 and you get y of x2 over here, and you get two equations for the two unknowns a and b, and you find the exact line that connects those 2 points. Okay? Well, that's a lot of work to figure out something that we already knew the answer to, but you know, it's good to see anyway, to test a new tool on something where you know the answer. So let me, I'll give you another example, which is the one I couldn't find a few minutes ago because I put the sheet of paper in the wrong place. So here's another example, and I know that there's some folks who are doing the, you know, the entrepreneurship and business, various minors and masters and all kinds of stuff. So here's one for the business world. So where you can use variational calculus to make more money. Okay? So if you use this to make more money and you go out and become rich, remember where you learned it. Okay? Okay. So okay. So here's the thing. So you start a company and you make a product. So amount of product is x of t. So at time t, you have an amount of product x in stock. Amount of product in stock. Okay? Now, you have certain costs. So let me say, here's example 2. You have certain costs. So for example, you know, so I'll give you a specific example. So my son, who's a high school student, found out that the company that his school was using to supply books to the students was charging a very large amount to sell the books and charging a very small amount to buy the books back at the end of the year. And then the next year they would sell them again for a large amount to the next year, etc. So my son decided, I'm going to do a better job. I'm going to buy the books back for more money and sell the books back for less money than this company does. So it's going to be a better deal for my classmates, and it's also a good way to raise money for his senior prom. That's what his goal was in doing this. So I'll put a very concrete face on this. So I know firsthand that when you have X books in stock, it takes a lot of floor space. In particular, in my garage, there's books piled up where he bought the books and then he sells the books the next year. Okay, so there's a certain cost. Well, for him, there's no cost, but for anyone else in the world doing business, there's a cost, storage cost. Storage cost is going to be proportional, let's say, to x of t. So you rent however much space you need to put your books, and the more books you have, the more space you rent. And let's just say that this cost, C1, is equal to A times X. Okay, so the cost of storage is proportional to the cost, to the amount of product that you have. Okay, and let's say that we have some boundary conditions, like at time 0, let's say you have nothing in stock. Okay? And then you get a call saying, at time capital T, I need to have an amount A of books or whatever product. Okay? And so then the question is, and this is one of the costs, I'll talk about another one of the costs in a minute. The question is, how do you maximize your profit, right? So how do you minimize your cost and deliver the same amount of the product? Well, let's say also that we have another cost, C2, which is proportional. So I'll explain this in a minute. So this is the cost to produce 1 unit. So the cost per time to produce 1 unit. So the faster you work to produce a unit, the more it costs. Okay? Why? Well, you know, if you're working really hard, people are going to get sick more often, or you're going to have to pay Federal Express to deliver it instead of the Postal Service, right? So the cost per time, the cost per unit is going to, let me see if I get this right. I'm not a business guy, so I have to get this right. Cost per unit to produce the cost per unit, the cost to produce 1 unit is going to vary with the rate at which you produce. And so cost per unit times units per time is going to be the cost per time, right? This is only the cost per unit. To get units per time, we have to multiply by another x dot. That is, units per time is x dot. Okay? So what that says then, if we say that, let's say that these are our only 2 costs. Okay? Then what we have is a total f of x and x dot, which is actually, you know what, we could make it even more interesting. We could say f of t and x dot is equal to, now the a's and the b's here I've left as constants, but you could imagine that these quantities could depend on time also, like the cost to rent space not only depends on how much space you want to rent, but when you rent it. Like rent could go up and it could be more expensive in the future and less expensive now, in which case A would be A of t, and likewise B could be a function of time as well. So you could have an explicit dependence on time in here, but for now let's just keep it as constants. So it's ax plus bx dot squared. So that's my cost function. And this is the boundary conditions. And we can put that right into the Euler-Lagrange equation and get a differential equation that will give us our optimal strategy. So let's put that into the Euler-Lagrange equation. First, partial f partial x dot is equal to 2bx dot, and then d dt of that is going to be 2bx double dot, and then partial f partial x is equal to a. And so what we get is that 2bx double dot minus a is equal to 0. Or x double dot is equal to a divided by 2b. Well, that's a pretty easy equation to solve. We integrate twice, and we get x of t equals 1/2 times a over b t squared. Plus, then we have, let's say, a constant c1 times t plus another constant, well, called c2. Okay, so this is the equation of a parabola, and we can find out what c1 and c2 have to be to match these initial conditions. In particular, x of 0 equals 0 means that c2 has to be equal to 0. And then if we substitute in t equals capital T, then we can figure out, we could say a equals, I dropped a 2 here. There was another 2 here, right? This 1/2 is because I integrated twice. And so we get a over 4b capital T squared plus c1 times capital T. So you can find out, you can solve for c1, and then you have your optimal strategy. Okay? So that's just another example where we can use variational calculus. So what does this say? This says, you want to reach A at time, so this is A at time capital T. You start out with nothing to begin with. It says it's better to do a strategy like this rather than, for example, in this context, with this model, a bad strategy would be work really hard, produce a lot of stuff, keep it in storage for a long time, and then ship it out at the end, right? That wouldn't be a good strategy, because then you're paying for space all that time. And if you're doing this, you have a high penalty on this term, and then this term will hurt you all the way along here. So in a sense, this is sort of like the, maybe the homework strategy that you go through in this class where, okay, here's where the homework is assigned, here's where all the homework problems are due, and you ramp up. Some people they do nothing and then they wait till the night before, but that's not a good strategy because because of the stress, right? So some kind of ramping up strategy like that is a good strategy in this model. Okay. Anyway, these are just two examples. One, a geometry example, and the other being this sort of business example. But the Euler-Lagrange equations are a really good way, well, they're the only way, really, to find the necessary conditions for an optimal solution for this kind of variational problem where you're looking for not optimizing at a single point, but rather trying to find an optimal trajectory. But we can use it in mechanics in another way. So for example, variational calculus in mechanics. So far we've been talking about systems that have discrete points and discrete springs and things like that. But we can also use variational methods for continuous systems. So for example, suppose I give you, and this is for a beam, or more a rod. So this is an elastic rod. Right, so an elastic rod is a continuous rod. So you might have it anchored to the wall like this. This is a continuous rod, say made out of steel, and you come here and you hit it with a hammer, and then there are elastic waves that will propagate back and forth along this beam. Okay? And so Professor Ramesh, for example, has a setup in his lab in the basement of this building where they have beams and they shoot at high speed a projectile here, and then it generates waves. And so for this kind of continuous system, we can write down a kinetic and potential energy, but instead of having sums over discrete masses and springs, what we will have are integrals. And it turns out that, so if we say that the position of a little slice here before any deformation is x, and then if this rod deforms a little bit so that this little sliver moves by a little amount u of x at time t, then we can write down the kinetic and potential energy for this rod. The kinetic energy is going to be 1/2 the integral over the length. So we're going to add up the kinetic energies of an infinite number of infinitesimal slices. The mass of each infinitesimal slice is going to be rho a times dx. So rho is the mass density per volume, a is the cross-sectional area, and so once you take the cross-sectional area times dx, you get an infinitesimal volume. If you take that infinitesimal volume and multiply it times rho, you get an infinitesimal mass. That's what this is right here. And we know that kinetic energy is 1/2 mv squared. This is the m part. This is the 1/2 part. The v part is going to be partial u partial t, and the v squared part is that thing squared. So that's what kinetic energy looks like for a continuum rod. And very similar to that in appearance is the potential energy for a continuum rod, and that's EA partial u partial x squared dx, where here E is the elastic modulus of the material, A is the same cross-sectional area, and the partial u partial x is essentially the strain in the bar. So if we go back to the discrete world, it's pretty much like what we've been talking about already, where you have a system of springs and masses. And in the case of a spring, we would have, if this is, we have a bunch of these x's now. Let's call this one xn and this one xn plus 1. So the potential energy here would be like 1/2 k xn plus 1 minus xn squared, just between adjacent masses. And this difference, as you look as the slices become infinitely small and infinitely close to each other, this quantity right here becomes this one. Okay? And the k is basically this. The sum over all such potential energies is like this integral. And so I'm just showing side by side the analogy. But the point that I want to make is that here you have a kinetic energy and a potential energy, but you cannot just take these and substitute them into Lagrange's equations and get an equation of motion. Lagrange's equations are for the case where you have a system with a finite number of degrees of freedom, and you get out of the kinetic and potential energy a finite system of ordinary differential equations. This will not give you a system of ordinary differential equations. The equations of motion for a continuous system like this will be partial differential equations. So you cannot use Lagrange's equations to get equations of motion from potential and kinetic energies that look like this. However, we can still use variational calculus to get an answer. Okay, so the point is that variational calculus and Lagrange's equations are obviously linked. We could get Lagrange's equations from variational calculus, but there are certain things that we can do using variational calculus that we cannot do with Lagrange's equations. And so here's how it works. So we define, so this thing that I mentioned before, where we take its derivative with respect to alpha and set alpha equal to 0. There's a shorthand for this, which is just delta I. And delta is called a variational operator. And delta has all the properties of a derivative, like the product rule and the chain rule, etc. And so what we can do is we can take a kinetic and potential energy like this and say that our I here is kinetic minus potential energy. And we can apply this formulation to this cost, which is delta of, actually, so over here, this is not quite right. So our I is going to be the integral from time 1 to time 2 of the difference of potential energy. Over here we have integrals, but those are not the integral in a variational problem. The integral in the variational problem is over time. So, and so what we're going to do is calculate this variation and set that equal to 0. That's like setting this thing equal to 0. And this is called the principle of least action, or Hamilton's principle. Okay, and so based on what we know about how this thing works and what we did when we derived the Euler-Lagrange equations, we can bring the derivative with respect to alpha, or equivalently this delta, inside of the integrals. Moreover, we can even separate the integrals out if we like. We still have a dt here. And then we're going to look at each one of these separately. So let's look at the t. So delta t, what is delta t? Well, if we take delta t, the delta can pass through the integral sign. It can pass through over to here, and we get a delta of this thing right here. And likewise, a delta of v, because the p and the a don't depend on u. Okay, they might depend on x, but just like when we did the derivation of the Euler-Lagrange equations, the alpha passed right through and acted on the dependence on the generalized coordinate and its derivative, but not on the independent variable. So over here, the delta will pass through over to here. Now, delta acts just like a derivative. So a derivative of the square of something brings the 2 down times the derivative of what's inside. So the 2 is going to come down and cancel the half. We're going to get an integral from 0 to L, rho A. It's going to be what was there originally times the derivative of what's inside, which is this. Okay. And then likewise over here, what we're going to get is an integral from 0 to L, EA. Again, the 2 is going to come down. We're going to have a partial u, partial x, delta of partial u, partial x, dx. Okay? And then what we're going to do, so again, delta acts like a derivative. Derivatives of smooth functions commute, right? So if I give you f of x and y, then, and I do partial with respect to x of partial with respect to y, that's the same thing as partial with respect to y of partial with respect to x. In other words, they're both partial squared, and the order here doesn't matter, right? Well, delta commutes with derivatives, so we can write this as partial with respect to t of delta u. And we can write this as partial with respect to x of delta u. Okay? Well, now we can take this right here and we can do integration by parts, like what we did before. So because I want this delta of u to be pulled to the outside. That's sort of the end goal of this kind of variational formulation. Because when we can do that, we can use a localization argument and then pop out whatever is inside the integral and have an equation at the end that we can then solve. So over here, if I do integration by parts, this is going to be, so I'm going to call this my, well, I'm using u here already, so u dv and all of that is going to be confusing, but let's just write it out. So this is going to be EA partial u partial x. So it's going to be the first times the delta evaluated from 0 to L minus the integral from 0 to L. Now I'm going to transfer the derivative over to here. It's going to be partial with respect to x of EA partial u partial x times delta u dx. Okay, so that's integration by parts. And the delta u, that's basically the epsilon that we had before. The delta u, well, okay. Let's just leave this to the side. Let us force this to be equal to 0. This is actually what's called natural boundary conditions. So if I give you a rod, what are all the possible statically determinate ways that you can put end constraints on a rod? You can have a cantilevered rod, you can have a sort of a stress-free end of the rod, you can have a displacement conditions on the rod, and it turns out for all possible statically determinate configurations of boundary conditions that you can place on a rod, this will be equal to 0. Okay? So let's say natural boundary conditions. Okay. So this term disappears, and we're left with this. On the other hand, this one up here, this is a partial t, but this is an integral over x. So we can't do anything with that. But if we go all the way back to here, we have another integral, an integral over time from t1 to t2. I've been sort of ignoring the integral over time and just focusing on the integral over the length for this term. But if we want to look at the integral over time here, dt, put another integral over here, dt. What we can do is switch the order of the time and the x integrals. So I'll just write down here, this is delta v. This is delta v without the time integral. Let's look at the integral of delta t dt. We can switch the order of the time and the x integrals. So I'll put t1 on the inside and the x integral on the outside, which means I have to put the dt first and the dx second over here. And now I'm going to integrate it by parts also, but I'm going to integrate it by parts over time instead of over length. So we're focusing on this inner integral right here. We're going to integrate by parts. And if we integrate this by parts, again with the integral over x on the outside, this is going to be rho a partial u partial t. It's going to be this times this, delta u evaluated from t1 to t2, minus the integral from t1 to t2 of, now we're going to transfer the derivative with respect to time over to here, partial with respect to t, rho a partial u partial t, times delta u dt. So we're only looking at the inner integral. This outer stuff is still there. But we've just done integration by parts on this inner integral, the 1 over time. Okay? Now, the thing about this is that this delta u is the same as the epsilon that we had before. Epsilon t1 equals epsilon t2 is equal to 0. So in other words, this one, so delta u at t1 is equal to delta u at t2 is equal to 0. And so this term becomes 0. Okay. And after we've done this calculation, we can go back and we can switch, if we choose to, we can switch the order of integration again on the L, or the x domain. And at the end of the day, what we get over here is these conditions. So we have this being one condition, and if we reassemble everything that we have, what we get is an integral over L and an integral over T. Let me see. Okay, so we'll write it all in one big equation. We'll keep the T on the outside. We'll put the L on the inside. And then this is going to be partial with respect to x, EA partial u partial x minus, now by the way, rho and a don't depend on time, so we can bring this all the way through, whereas for the other one that involved this, it could be that the cross-sectional area or the modulus of elasticity might change as you go along the rod, if it's not a uniform rod. So we'll keep that on the outside, but these quantities don't depend on time, so we can bring this all the way inside. So this is rho a partial squared u partial t squared, and this is all times delta u times dx. And then we had these natural boundary conditions, which were EA partial u partial x times delta u from